There we go.
Still says photo.
But it's showing 6 seconds.
Okay. Very sure.
Well, welcome. Sorry, this has been a very traumatic time for a lot of people, especially when we've had Lloyd basically operating this system, but it's great to learn it, and now I think we have it. So thank you for coming. I know you came here for the pizza, not to learn about threading, so enjoy your pizza. And I did speak in February, and it's a pleasure to speak with you guys again. And I just want to say a word about our sponsors. Fortunately, we are blessed to be in the Microsoft area, but a lot of groups that are sponsored by Microsoft don't usually last without sponsors. And so I want to thank you for your indulgence. I had a person send me an email saying that he wasn't interested in the jobs, but we want to have everybody know that without our sponsors, C++ would not be still alive and kicking. Another note that I like to make is that this is an introduction. So basically what I'm trying to do is talk about all the different aspects that I need to look at in order to successfully pull this project off. I was planning to do this for SG14 last year, but as I started working on it and seeing the complexity of it, I was like, okay, I don't really think I can start doing that right away. So, what do I want to accomplish tonight? Well, first of all, I want to examine all the components that affect thread management. The second thing I'd like to do is to explore what exists in the hardware, software, OS system, ecosphere, to see how to better utilize those environments. Third thing is to create an STL container that would interact with the OS and hardware, that would have interaction that is used to control thread synchronization, and to work with various hardware and memory configurations. And finally, to improve efficiency of processing multiple threads. In today's environment, basically we have processes and threads that are basically put into an OS. The OS has some variables that it writes to, and then it's basically put into a hardware environment, and it's run basically so that there's a static one-time setting of the process variables that operate the threads and processes. And I'm not talking about, okay, we would need a file or something like that. Yeah, that has to deal with kernel, but I'm more talking about operating a thread so that it will dynamically use the environment efficiently to perform better. So my idea of a model would be to have sort of a communication between the three different systems where process and threads and OS and hardware can all dynamically interact with one another to be able to make sure that there's better performance. So what has been done in the past? Well, we have starnix space C, and people are saying, C, this is C++. Well, yes, that's true, but C++ is basically looking to standardize what is currently being done in the C world. So, the first thing is that starnix base C considers threads as lightweight processes. It creates a thread using a pthread underscore type method. It destroys threads via join or exit call. Oops, man. can perform stack management. You can define how big the stack size is for your particular thread or process. But however, it still has dependency upon the OS and hardware. And it supports multiple synchronization types like mutex, condition variables, barrier, reader-writer locks, spin locks. Oops, getting a little ahead of myself. We will go through some of those later in the presentation to define those better. So what is currently in the C++ standard? Well, as we know, next year we're planning to come out with C++ 17. And so in the current document N4582 in section 30, we have a listing of the objects that C++ will be supporting. And basically, if you look at the C++ 17 and C++ 13, there's a slight difference, but not much. The first object that we would like that they support is the thread object. They support mutex objects, condition variables like wait and notify, and they also support asynchronous types called futures. I love to hit that mouse wheel. Anyway. And so basically, this is the thread object that C++ 17 has. Let me zoom in there so you can see better. So basically, we have an ID, we have the constructors, destructors, copy constructors are deleted, and the move operators are still supported. Swap, joinables, and etc. Another thing that's being supported by C++ is concurrency. There is a new proposal out, N3666. I'm not sure if it's new, but it's out there, where they have support for latches, which is basically an internal counter that blocks threads, and then when it reaches 0, it basically releases all the blocks. However, it cannot be reused, so you have to recreate when you're wanting to use the latch again. Barriers. Barriers are thread coordination mechanisms that optimize memory access. So basically, you have to, if you have a number of threads operating, everything has to reach a particular point before the next step occurs. And also, these barriers can be reused. Another big emphasis that Microsoft or C++ is trying to push is lock-free. And so they are working a lot in atomic smart pointers to utilize the hardware that has locks that are similar to these commands in assembler. And the purpose of a atomic smart pointer is that it does a cache lock rather than a bus lock. So therefore, it is less of a penalty in performance because you're basically working with memory close to the operation versus a bus lock that would lock access to the RAM. Also, Boost is coming out with or has been working on a lock-free, and they basically provide a number of data structures or policies to provide non-blocking performance. Parallel. This is also another hot topic that SG14 is definitely getting a lot of interest in because we're working with game programmers, trading companies, things like that, who work with environments where high latency is definitely a no-no because it will definitely affect results. And so basically it's multiple execution cores for processing. And some of the architectures that are currently out there are multiple CPU cores, SIMD, which is single instruction, multiple data. Then there's parallel computing with multiple instruction, multiple data. And there's even some that, like, it's been used with the space shuttle with multiple instruction, single data. And I was looking at an architectural magazine, and there was like reusable inputs, things like that. So there's a ton of different types of architectures. And C++ is trying to develop a language to support all of the above. Another hot topic, in which we even had our own meeting here in January to talk about coroutines. And basically, coroutines allow one process to communicate to another process that it yields its control so that the other one can start executing. And it's also possible to send data as results back to the threads, or communicate between the threads. So now that we've shown what is currently existing, now I'm trying to discuss what I plan to propose. And so we need to look at the design decisions and what aspects of the computing environment that we need to look at in order to solve this problem. And so basically, I'm looking at the influencers that will affect the dynamic multi-thread synchronization. One of the influencers is hardware. Another is the memory. The third is the OS scheduler, or basically the operating system. Another is the process, the application. Linux looks at threading as lightweight processes, where Windows looks at a process and has a lot of information stored in that particular structure, including threads. And finally, threads. How do we store, or how do we handle that, and how do we make that more efficient with more characteristic data? So let's look at hardware and look at different platforms. We have the 32-bit environment, which is still active. The x86 and ARM processors are out there. We have the 64-bit environment as well. We have multi-core, GPUs. Whoop. I should have taken it out, but hey, what the heck. We're really spinning here. So, and general purpose graphics processing units. Basically, that's a combination of CPUs and GPUs. We have field programmable gate arrays that you can put an ARM core on or something like that. And we also have multiple instruction, multiple data. So how does 32-bit handle multi-threading? Well, it has a bunch of segments so that we can reuse memory, base memory. So when it's doing task switching or something like that, it basically says, oh, this application is running at this code segment, but still use the same memory location as maybe another application had, but now we have a different code segment. We also had the descriptor tables, global descriptor tables that had a location for the interrupts plus other applications. And we have the local descriptor table. ARM also supports multitasking, which basically means that we can do more than one task at a time, or almost in parallel. However, the concept of multi-threading is not supported as that philosophy. But it does have different registers, and it uses R13 as the stack. For the x64 environment, they eliminated the segments because now we have 10 to the 18th address spaces. However, we're still constrained by the memory. ARM did add more registers and more instructions, but yet it's still focused on embedded, where multi-threading is not I mean, if you look at your phone, you're not doing multiple tasks at the same time on that particular environment. Execution units. This is important because how many execution units we have is how much parallel and how much less invasive a thread is going to be on the stack or the heap memory. Basically, an execution unit is a fetch, decode, execute processor, and a single core only has one of those, while a multi-core has many execution units. Here we have 2, but they're getting up to 8 and 16 and 32. And we need to set the affinity for the thread so that it will operate only on one processor. That is the rules for the user threads. And there's 2 ways to supervise operations. One is called symmetric multiprocessor, where basically a program can use the same memory and operating system, but yet it's spread across all the cores. Or asymmetric multiprocessor, that basically an application runs only on one single core. So we also have GPUs. So we could have a system that has like a GPU, which basically has a CPU operating, doing preemptive multithreading, whereas with a GPU, because it doesn't support interrupts, which I got all the way down here, it doesn't support interrupts or exceptions, that preemptive multithreading is not supported, so we have basically a yield state, based like a barrier, saying that once the next calculation is completed, that we have, and yet we're having multiple fields inside that particular memory block, that we have to wait until every operation is successfully completed before we go to the next set. But it is very high speed, and it does have threads in it so that we can do multi-threading in order to do calculations quickly. As I was just talking about, the combination of the CPU with the power of SIMD of the GPU. So therefore, we have a control, arithmetic, logic units, cache, things like that, that basically can send data to different environments, but yet we do the calculations over here. Another thing that we were talking about in SG14 was programming field programmable gate arrays. This environment, like I said, can have an ARM or some other parallel processing core put onto that particular environment. And it can also be made as a separate entity from a controller that basically, like I was watching a video that showed how a FPGA was controlling the arms of a robot or legs of a robot, but yet there was a CPU or embedded system controlling the environment around that FPGA. So what does an FPGA basically look like? It looks like the internals of a processor. We have these logic cells here with all these networking I/O wires that basically perform logic in the lookup user table here, which is basically a multiplexer of the inputs with a DQ flip-flop and an OR gate there that basically provides a 1 or a 0 based on the logic that is programmed by the developer. We can also have environments where we have multiple instructors and multiple data, like in a grid computing. However, we have to very much worry about how accurate we want the data. So we need to synchronize data between processors in order to ensure correctness of the results. So here's an example of a MEMD where we have multiple processors getting data from one source here and sending it out. But if we want to make sure that if we have processor A or B getting information from processor A before it can go on, then we have to make sure that that is synchronized. Otherwise, we can just take a parallel and do processing independently of each other. So all these factors is necessary to figure out how to support threading so we can dynamically support what kind of locks or synchronization we need to put into that or support. Okay. Another consideration that we need to consider in our influencer, to consider in our memory or lock synchronization model is the memory. We need to figure out how fast and location. For example, registers, they work very closely to the CPU core. However, they're limited, so we need to figure out how to best use that asset that is provided to us. Cache. How large is it? Sometimes they say, well, if we want to handle an image that is 64 megabyte, we may want a 64 megabyte cache because we're worried about the fact that there may not be enough data to process that quickly. And there's 3 different types of cache, especially in the Intel processors, L1, L2, and L3. We also consider RAM, how large and how fast. Back in the days, we only had a few kilobytes and everything moved very slowly. So as we're getting larger and larger with RAM, we're also getting much faster. We need to consider how large our stack is and how large our heap is. We can also consider a GPU configuration if we have to utilize that particular environment in doing the processing. So let's look at some topics here related to registers. So they're the memory units that are closest to the execution unit. So they're very fast to access, yet very limited in number. Intel has a quote CISC base that supports 32-bit, 64-bit. They put an R in front of the AX, whereas 32-bit they use the E in front of the AX, etc. They also have the MMX for multimedia, the XMM for SIMD, and they support floating point registers. As you can see in this image, the general purpose registers stack. Here's the XMM and floating point MMX. So I know I'm boring you guys, so you better get more pizza right now. So also ARM has basically a number of processors, or a number of registers, excuse me here. And they use R13 and R14 for different interrupts in the supervisor mode, whereas in the user mode they have 15 here, where they have the R13 being the stack, and the link register is 14, and the program counter is number 15. And they support FIQs, and these last 2 points require to be in supervisor mode.
FIQ?
Whoop.
Using TLAs without defining it.
FIQ.
FIQ.
Fast interrupt. No problem. Oh, what happened? I'm losing something here. Stack. It's usually top down or subtracting. Each process is allocated a segment of the stack. So a process has maybe like 4 megabytes assigned to it, and then each thread has some subsection of that particular stack. Like I said, it's very fast to access, and variables are deallocated when a function or process ends. So it's very clean to work with. And space is managed efficiently by the CPU. Here's an example of a stack pointer that's basically pointed, and when we push an EAX, it basically subtracts down 4 spaces because we're working with 32-bit, yet each space is 8-bit. So then the stack pointer is pushed down, or is decremented down. If we wanted to add another element, then we would again put it below the first element and then move the stack pointer down. And the same thing with popping. If we popped the EAX here, then the stack pointer would go down to here and the EBX would go up here. And those are basically, those are registers, so in case you wanted to know, so let's see what I'm asking you about. Heap. Heap is also important because some memory variables can be put into global, or a global location. So it's basically, we have to consider its size. It can contain large memory for single variables and is accessible throughout the lifetime of a process. However, it needs to be explicitly deleted and can lead to fragmentation, which causes problems because if you want to assign another large variable and there's not there may be a space, there may be enough space, but yet there's a block in the middle, then we have to worry about reassigning the first memory to be located in a place so we can get a large enough chunk for another variable to be put in place. So basically, like I said, the stack is subtracting or goes down and the heap climbs up. So cache. Cache is another very important memory consideration. L1 is local to the processor core. L2 is shared between 2 cores on the same die. And L3 is shared between all cores. And for synchronization, it uses read and write fences to synchronize data flow. However, one of the issues is, like I was saying earlier, if you have a 64 megabyte image and you only have 32K of memory, you're going to get a lot of hit miss where you're looking for a particular memory value, but it's not there in the cache, so then you have to go to the RAM in order to find that particular location, and therefore that is more costly than just going straight to RAM. So here's a diagram of where those caches are. Here's the L1 cache, the L2 cache, and the shared cache between all the different cores. GPUs have their own memory. Local on the chip is that they have register and shared. And those that reside off the chip are local, what are called local, constant, texture, and global. And basically here we have shared memory that can have different configurations, and then the L1 cache will be whatever is left over. So basically, if we look at shared memory, we have this very fast accessibility to these particular byte ranges in this particular area for a particular thread. The next thing that we need to consider is the OS scheduler. There's various algorithms to handle process and thread execution. One of them is called first come, first serve, round robin, priority queues, multi-level feedback queues, and the lottery system. However, we want to avoid deadlocks or live locks, which is basically occurs when a algorithm that's trying to prevent deadlocks constantly triggers. And so most operating systems use preemptive scheduling in order to prevent that. And there's 3 types of scheduling. There's the long-term, medium-term, and short-term schedulers, which are all, so basically we're looking at this to say, well, if we have this particular environment, how is this thread going to be handled so that we can efficiently figure out a solution? The long-term, any questions? Okay. Is if the OS uses preemptive scheduling, then the long-term scheduler does not exist. However, if it does exist, all new processes will be determined for admittance by the long-term scheduler to the process queue. This scheduler balances the jobs between I/O and processor-based processes. And it loads the process by allocating memory and setting variables used by the process. So here's a little diagram here. So basically we have a job that's put into the batch, and then the long-term scheduler will try to determine what to put into the ready queue. The medium term scheduler basically removes processes from memory. So after they've been used or swapped by the CPU for another thread, they are going to suspended state. Basically, it removes the memory from those processes so that it will have enough memory in the CPU for the threads that are being used by the CPU. And also the short-term scheduler, which basically takes items from the ready queue and starts to run them in the CPU. So what are different execution scenarios? One is the process. I mean, that is the main execution unit for an application. It stores all the information to successfully operate an application. It stores thread information like interrupts, or thread information like interrupts and other information that will be used by the application. And in Linux and Windows, this information is stored in a structure. So this particular process is similar to what a Linux environment would show, where it has variables, like counter, timeout, ID. It has a bunch of task structures that basically say, this will be the next task that we fired, this is the previous task that we fired, etc. It contains file information basically for accessing files that will be used by the application. And it also has a thread struct and a signal struct. And the signal struct, if it's set to 2, the thread or the process can be asynchronous. In Windows, however, their overall structure are called eProcess, which is a wrapper for everything about the process. So here we see like the kernel processing block and other information about a process. And inside this struct is called the K process, which is basically the kernel portion of the process that basically the OS defines how the application will run on the hardware. Linux basically operates in user space and uses syscall to a very limited amount of syscalls to the kernel to access information from the hardware or the OS. And again, as I said earlier, it also considers threads as lightweight processes. The next execution unit to consider is the thread itself. Each thread has stack allocated to it. As we see here, we have stack, we have registers, and it has access to code, data, and file information. The thread also contains information about the I/O devices that will be used by the thread, whether the thread is synchronous or asynchronous, and it contains information about the two access levels. Again, kernel, which is the most protected access, and user, which is basically the general access. And the kernel is defined by the OS, as we see here. It's slower to create and manage, but the OS creates them. And therefore, it's specific to an OS. So therefore, if we have a kernel running in Linux, it will be different than a kernel running in Windows. Maybe not totally different philosophy, but there are some major differences. It can be multi-threaded and uses a hardware protection level of 0 to 2 to make sure that user level threads cannot access indiscriminately the hardware or operating system values. And so here's an example of the K process, which is used by Windows. It has a bunch of lists here for ready, threads, processes, and profiles. It has an entry into the local descriptor table, as well as has a value or knows where the interrupt descriptor table is. The user threads. It's an object created by the threading library or by the code, whereas the kernel is created by the operating system. It can run on any operating system. However, it can only operate on one processor. It can run independent of the kernel. However, it uses cooperative multitasking, which means that one thread blocks all the others. So when one thread is being used by the user level, all the other threads are being blocked. And it has a descriptor privilege level in the hardware of level 3. So here we have user space, which is the thread library, and we have the kernel space, and then we have the CPU. And there's a relationship between kernels and users, threads. There's many to many, many to one, and one to one. And Windows uses this one to one. So what is many to many? First, it's multiple user level threads that have the same or smaller amount of kernel level threads. As we see in this image, we have user level threads, and basically when a kernel level thread gets available, it will attach to it and start executing the process completely. The number of kernel level threads are managed by the operating system. Many to one, multiple user threads access with only one kernel thread. So we have here a diagram of that. It's more secure because now we have only one thread to worry about. However, and eliminates race conditions. However, it may cause deadlocks because if it gets stuck with one of these threads, then the rest of the threads can't operate. One to one. It's better concurrency and support for parallelism. Like I said, Windows uses this, as you saw in the structure. There's an E thread and a K thread, and the E thread contains the K thread, but basically it's two separate threads that are operating. However, there's a disadvantage to that is because we need two threads created instead of one. And also for large tasks, we have to rely on one thread to do the work. And we may need, what if we could do like multiprocessing on the kernel layer and then have one thread access multiple kernel threads. Another thing to consider is synchronization. If we have shared data, we have to consider how we're going to synchronize it so that we don't have race conditions. So we have to look at locking mechanisms. One is the semaphore, another is the mutex, another is a barrier, auto locks, and the spin lock, like that. So we need to make sure that the data doesn't get corrupted. So how do we do that? Can we use a semaphore? Well, what was semaphores originally? What the original purpose was to let ships know, hey, we're going in the harbor, we're leaving, we're doing something else. So basically, it has signals that can communicate to other threads or processes that some status is changing. It uses a counting process to make sure that there's enough resources for each thread to execute. The main purpose is to control I/O access in operating systems. They're portable and usually efficient. Here's basically what a semaphore does. It basically increases the counter when we access the semaphore and we're using a particular thread. And then it will also, when the thread is finished with its operation, it will decrement the counter and let other threads know that there's another lock or another resource available to use in order for it to operate. Here is an example of a producer-consumer model application where we have an empty count, which is basically how many empty slots do we have in a particular queue. And then we lock by setting the use queue to 0. That way, no other thread can access this particular queue. And then we put an item in the queue. Then we increment the use queue to 1 to let other threads know that we have availability to operate. And then we increment the full count by 1, saying that we have something to consume. So, and then the consume is basically opposite. It looks at the full count. If that is available, then it will decrement the use queue to 0 and then get the item and then release the lock and increment the empty queue because now we are empty count because now we have one more empty spot. Mutex, well, this is a mutual exclusion lock, and basically what we saw here is an example of that. It's a binary semaphore which has 2 states but 1 resource. And only one thread will have access to the resource after it's been locked, and the others will wait. So here we see a code for that, where we basically set the the state of flag to 1, and we check if it's 0 or 1. If it's 0, then we just keep looping through. If it's not, then we or if it's 0. If it's 1, then we decrement it to 0. We check if it's 0, then we go into the segment that we will be doing our processing. Once we're done, we will release the lock and increment the mutex back to 1, and this is the end block for that.
On that slide,
Yes.
it's a common misnomer causing a lot of problems in the industry. A mutex is not a binary semaphore.
Okay.
Mutexes have ownership. Semaphores, anybody can twiddle the count on.
Okay.
Mutex can only be released by the owner.
Okay.
It makes a significant difference in how you screw yourself up.
Okay. I appreciate that. So again, you're Chris, right?
Yeah.
Okay. So Chris is saying that this is a binary semaphore is a misnomer here, and that we should say that we have ownership of a particular resource when we're doing our synchronization. So, thank you. So basically, here's a pictorial example that we have some shared data here. The thread 1 is accessing it, and it will send a signal to block T2 from accessing that shared data. Then when T1 completes and yields control, the opposite will happen. So T2 now has access upside down. I don't know how that happened. And it will send a signal that will cause a barrier so that T1 cannot access the shared data. And this is important because we want to make sure that if we're doing one addition or subtraction of a variable, that we actually have the correct value so that the next thread will not get that value that was the original value and actually give the wrong result. Barrier. Well, barrier is basically optimizes access to shared memory. So basically, threads are required to wait until all threads reach a certain point, the barrier. And this is similar to as if you went to a restaurant and the waiter would not seat the party until all the members of that party came to be seated. So here is sort of a pseudocode here that while we're waiting or while we're processing, we have a before barrier 1 that once we reach that, then we increment this value, and then we get ready to analyze the go function. The same thing here, we have before barrier 2, and then we increment this, so we could have 1 and 2 as the value, but then when we go through this block, we decrement that so that when that finally reaches 0, then we can start processing a particular piece of code. Auto locks. This is basically an abstracted mutex. Once the locks, as you were talking about ownership, comes into scope and then unlocks it when it goes out of scope. And so basically here's some code that was written. So we check if the state of the mutex or if the object of the mutex exists, then we lock it. And then when we leave the object, we use our destructor and test for, again, the object and unlock it once we leave a particular code segment. Any questions? So spin locks, this is very important because sometimes people say, well, if a thread's not being used, put it in suspended state. However, putting it in suspended state means that we have to store all the on the stack the registers and other flags, and then when we wake up, then we have to reprocess that. So here, a spin lock keeps the thread active and basically makes it wait until a resource, go into a loop to test if other resources are available. And then when it is available, it will start processing. So therefore, like I said, it requires fewer resources to block that thread. And it's better than putting the thread into suspended state. So here's Linux C, which basically creates a lock, and it will put that lock in a spin lock until finally that resource becomes available. So now that we've gotten through all the grind of trying to figure out what are the influencers, what is the proposed solution? Well, one of the things that we want to do is look at the thread object. We want to add more characteristics to the thread so that it can be modified by the OS or the hardware, so that we can dynamically adjust variable or adjust the stack size that it uses, or the heap that it's using, or some other aspect of the thread that we can either maximize or minimize to better have that thread utilize the resources better. Also, we would have a dynamic lock. So rather than relying on one lock model, there could be multiple lock models that are supported by one object. As I was saying, it would be nice to have the processing thread communicate with the OS and back and forth, as well as with the hardware back and forth. And the third thing that I would like to propose is a STL class that would hold the thread and dynamic lock, so that it could dynamically communicate and adjust each of those objects. So let's look at the thread object. What are some of the additional features that we would like to add from the existing C++ standards? One, let's do a volatile unsigned int for CPU affinity. Also, code size. Let's say that you're doing A equals B plus C in a particular and you're synchronizing that particular calculation, rather than making a whole stack size of 1 megabyte. Maybe if we had a small code size that was operating in this particular situation, that we could reduce the stack to 20 kilobytes or something like that. Again, we would have a stack size that would be adjustable. The priority, maybe A equals B plus C has a higher priority than something that's pulling from a file, so that's something to be considered. The thread state, is it suspended, is it active, is it ready? And also a threshold variable. What will cause this thread to shift synchronization objects from one type to another? And also looking at the time and ticks that occur in so as the thread is operating, we would like to see how long it took, and we would like to update that as we're processing. And of course, as I said, this is an introduction to this particular philosophy, so therefore there's probably more characteristics to look at. The second object is called dynamic lock. It would take a template of a bunch of arguments that would be volatile. I should have called this dynamic lock, but I might, whoops. And it would contain argument of initialize a list of variables. This is not supported by C++17, so this would be needed to be considered. And one of the examples of this would be how many CPU cores is this particular application running on. We would have the security, and then we would have basically lock and unlock. The next object that needs to be proposed is the STL that would contain the threads and the dynamic lock. One of the things that it would contain is the next thread that is free to be used to process. It would also include a weight variable. So if we keep adding threads to this, it's going to be adding more weight, and therefore we need to figure out the synchronization of that due to the changes in how many threads we have. That's one example. Of course, we have the usage of the dynamic lock. We would have a container for threads, and this is something that has been discussed, not this part. One of the issues is that in games, when we're dealing with STL containers, they are afraid of exceptions being thrown. And so they use a lot of what they call no except when they're writing their functions. So therefore, it will not throw any exceptions. So what will happen is that if a game is reaching a point where allocation of objects is reaching maximum and finally goes above the limit, that the game basically exits on its own. So I was trying to think of some other process that we could use to basically allow a background thread to be kicked off to do some work so that a game can continue on forever. And so this would be what I call it would be a container for futures and an async container. And then we would use these two, these two methods, utry and ccatch, to basically perform this operation so that utry would say, when I reach a particular threshold, I will fire off a flag that the process itself, not an interrupt, but the process itself will trip and will execute or iterate through this list and start doing background processing. And of course we have the add thread, remove thread, and other aspects of the STL that would allow more threads to be added or removed. So what's the execute function basically going to be looking like? So basically, as I said, we had the utry. The utry would be basically a function that would be surrounding the function pointer of how the basically how the user would like to see the threads be executed. And then if the utry says that there was some issue like not enough memory to add a whole nother set of objects, that it would kick off the ccatch, which would fire off the sequence of futures, like clean the stack, reallocate memory, and write to the log. So let me give you some examples of how we would implement this. The first example I'd like to do, again, we go to the producer-consumer model. And here we have a production of a widget, but yet in inventory we have 15. So if a consumer orders 10, rather than using a full-blown mutex or barrier lock, maybe we use an atomic lock, so that we only, for one cycle, basically subtract 10 from 15, and then the next cycle start kicking off production again. Another example would be, let's say that a customer ordered 30 but didn't mind getting shipments of 10. So here we would have, again, like the original model, they would get their first 10, but then we would put a lock on the consumer to make sure that they weren't taking stuff away before this thread finished with building another 10. So therefore we could use something like a barrier or a mutex or something that would allow us to control the fact that we don't want the consumer to access the inventory until we're done. The third example is, again, the customer orders 30, but they want all 30 shipped at the same time. So again, what kind of model can we use, and how do we figure out from that model what kind of synchronization object that would be most efficient to make sure that this process occurred quickly? And again, as I was talking about gameplay, in the U-try, we would have execution of threads. And if there was a situation where they wanted to clean up memory or write a log or do something, that in the background asynchronously, as you see the different timelines here, I should have put timeline here, that they would operate asynchronously while this was operating in the foreground. There's other scenarios that we could put into place, or that would be examples. For example, what if another production line was put in place? Maybe we would put a spin lock so that we would wait for resources, so that if one had the resource, the other one had to wait until that resource was let go, but we could just use a spin lock. Also, we could use the heap memory with a constant pointer volatile data so that we don't even have to worry about locks. Oops, back. Sorry. Or another one is if two customers order, one customer needs to order in a hurry, and there's a limited supply. Maybe we would put, and the second customer, it wasn't in a hurry, so we could put a latch on for the second customer and a mutex for the first. So I know that you're probably saying, well, how are we going to do this? Because OS, that means that we have to coordinate with OS and hardware vendors. Well, just recently in a forum, a member of the C++ committee was saying that we don't have direct influence over OS and hardware vendors. However, somebody wrote that, yes, we do, but it's not in a direct way. However, people like Intel, or companies like Intel, are very interested in what C++ is trying to propose. So here's my references. If you want to do some of your own research on what I was doing, I'm sorry it was very tedious to go through all this, but I appreciated your time. Thank you. Any questions? Questions? Yeah, go ahead.
So the template which was proposed for C++ standard,
Yes.
what is the thinking behind of using these doubles? Because standard's supposed to run everywhere. How we're planning to deal with the platforms which don't have forward-deployment communication?
So let me repeat the question. So how do we deal with platforms that don't have support for double? Well, I guess from my study of chaos theory, the more we know, or the more finite we look at things, the better we have an understanding of what is really going on. But that's a good question, and that is something to consider, because maybe we put a lookup table or something that would say that this integer value would be similar to.
I think it is a good question. It's more general than just double, because it happens all the time. You have to decide what you have built in or what you have to dynamically choose and load.
Right.
So it's always very interesting design decision. So I was very curious what you're thinking about this.
I'm very, that it was something that I was thinking about a couple years ago, because again, floating point is very dependent upon who's writing the library, and it also is dependent upon the environment, because let's say you have 32-bit floating point, but you only have an 8-bit processor. How do you handle that? And so therefore there needed to be the ability to dynamically adjust a particular variable to handle that space. That's not really part of this particular discussion, but you're right about looking at it at dynamics, since I'm already talking about dynamically handling locks. Yeah, that I appreciate that. Any more questions?
A matter of terminology, the thread class that you displayed, you identified as part of the STL, the standard template library,
Yes.
which I understood to mean just some subset of the standard C++ library having to do with containers and iterators and callback functions and stuff like that. That why did you use the term STL for this seemingly different piece of the standard the proposed standard C++ library, which deals with threads?
Well, okay, so the question is, why do we use STL when we already have a quote, a thread object? Is that what you're saying? Why?
Well, it's not. I don't think of the thread abstraction as part of the STL. It's part of it.
No, but the STL.
C++ library, but the STL is a subset thereof with a particular structure.
Okay, but it's a container of the object, and basically, I think right now standard template library is being expanded because of like game programming. Like a lot of what you'll see today is that they've come up with these single level arrays or something like that, where basically they separate the one value or an array to find some value and then the value itself. So they call it the same kind of like STL container, maybe with a modification to that. But I think STL for like game programming has been modified. I'm sorry, I hope I'm answering your question, but it's been modified a lot because they're trying to do low latency lookups for things. So STL gives me flexibility to have a container, and inside that container I can define what I would like that particular container to.
Using the standard STL functions like define and iterate and
Yeah. Well, I mean, you got to find. You mean when you're executing, maybe you want to find the thread that is available next to, so that when the resource is available, it will just start firing that particular.
So a thread is something you might put in a container.
Correct.
But the thread is not the container.
Right. That's correct.
You know, you can put anything in an STL container. That doesn't make the thing that you put into it part of the STL.
I see what you're saying.
I understand your terminology here.
I see your.
What's STL and what isn't?
I guess because I'm using containers that store that particular object inside this particular class, so maybe.
You can put a double in a container, and that doesn't make double part of the STL.
True.
Technically speaking, the term STL was pretty much officially discontinued like 15 years ago.
Well,
It's semantics, you know. I mean,
Because I taught a class I was up here 15 years ago teaching about STL. Back when.
I guess the point is that I'm trying to say that we have STL to collate these kinds of objects, and we can make a class that utilizes that capability. So, but thanks for your question. Any more questions? Come on, Cliff, wake up. Yes.
So you mentioned multiple instructions, single data, and I think you even mentioned space shuttling.
Yes.
So can you explain that?
So basically what multiple instruction single data did was it took data from multiple sensors on the space shuttle and basically performed a number of operations on that data for each. They had like 5 different cores or processor units on the space shuttle to basically guide that, use its guidance system to steer it, and also to let know that like heat sensitivity and things like that, so it would say, oh, I need to pitch or yaw based on the particular sensors that I'm looking at. So basically all these units would take the same data, process it, and then basically do a poll, and whoever was the highest in that poll, that's the way the navigation unit made its decision. So.
Is that a singular case or is that general?
Well, it's also used for image process. There were some cases for image processing. But however, it's very expensive, but it's something that definitely something that I would be very interested in for doing very accurate image processing and graphics. So, yes. Anybody else? I thank you for coming. Sorry that it's a lot of material, and it's something that needs to be looked at. And I appreciate your time and coming. Thank you.